I want to just drop you directly into a scenario right off the bat. It's a moment that, I mean, basically every single person listening to this deep dive has either orchestrated, witnessed, or just suffered through.
Oh yeah, the inevitable moment.
Right. So picture a carefully designed industrial enclosure. We're looking at it on a high-resolution display rendered in that pristine, shadowless gray the CAD software uses.
Yeah, the one that makes everything look incredibly authoritative.
Exactly. It projects this aura of absolute certainty. The structural ribs are perfectly spaced, the thermal management vents are just mathematically optimized, and nestled in the lower quadrant is this beautifully integrated service panel.
Every vector has a purpose.
Yeah.
Every clearance has been verified by some collision detection algorithm.
Right, so we pull up the technical drawing for this assembly, and the documentation clearly indicates adequate tool access. The geometric dimensioning is justified, the tolerancing is justified. From a purely analytical standpoint, it is just elegant. The system has told us that a standard tool will fit the fastener behind that panel, but then...
Then you cross the threshold into the physical world.
Exactly. A technician on a noisy, probably poorly lit shop floor takes the specified tool, reaches through that access port for the fastener, and the tool simply cannot rotate.
Because a physical cable harness, which, by the way, was also designed by someone and is absolutely supposed to be there, is currently occupying the precise working envelope that the tool requires to turn.
So here is the question that sets up everything we are unpacking today. If the physical dimensions of that panel and that fastener perfectly satisfy the technical drawing, is the design wrong?
I would frame it a little differently. I mean, the design isn't necessarily wrong in its local logic. The drawing simply answered a much smaller question than the technician needed answered.
A smaller question.
Yeah, the drawing answer, does the geometry fit the space? But the technician, they need to know, can a human being actually operate within this space under operational conditions?
Which brings us to our real mission for today. Whether you're an advanced student mapping out complex systems, or a practicing engineer dealing with supply chain variations, or, a technical leader just trying to get different disciplines to actually talk to each other, you have lived this friction.
Oh, intimately.
That specific, agonizing moment when a mathematically elegant idea just collides with physical reality. So today, we are immersing ourselves in field note number 009, Why Engineers Fall in Love with Reality Instead of Ideas.
And we need to set some ground rules for this deep dive right away. We are entirely discarding that traditional exhausted theory versus practice debate.
Please, yes.
That framing is just a crutch.
Yeah.
It assumes this adversarial relationship that doesn't actually exist in good engineering.
Right. We are looking at how engineering ideas actually transition into dependable systems. We're going to examine how modeling, prototyping, verification, validation, and operational observation all link together. And the tension we're going to return to over and over is a question of loyalty. In engineering, do we protect the original idea or do we protect the outcome?
And that question of loyalty dictates how a technical organization handles bad news.
Yeah.
I mean, it dictates how they handle physical evidence that contradicts their beloved models.
So let's start inside what the sources call the sanctuary of ideas. Think back to that technical drawing in our intro. That drawing was an idea, and mathematically it functioned flawlessly. And my initial instinct, as someone who, relies heavily on analytical efficiency, is to defend the model.
Naturally.
Because without abstraction, how could engineering possibly scale?
It couldn't. It just couldn't.
Right. We cannot build a full-sized, flight-ready passenger jet just to test a single aerodynamic flutter equation. We can't pour a concrete bridge pier just to see if our rebar spacing calculation holds up against a theoretical seismic load.
No, you'd bankrupt the project in a week.
Exactly. Models are incredibly generous environments. They grant us perfect isotropic materials. They assume users who actually read the manual. They exist in stable environments with purely axial loads. When I am in the simulation software, a fastener stays exactly where the coordinate system placed it.
It doesn't back out because of vibration.
No. This analytical efficiency is the only reason we can reason mathematically and achieve early design confidence before we commit millions of dollars to capital expenditures.
And I completely agree. The ability to abstract is the foundational superpower of the discipline. The physical world is just staggeringly complex. If a structural team had to account for every micro variation in ambient temperature, every slight deviation in the grain structure of a metal alloy, and every subatomic interaction simultaneously.
They'd freeze. Nothing would ever get built.
Exactly.
Yeah.
Models allow us to aggressively filter reality. We isolate specific, manageable relationships. We can push a simulated material through 10,000 stress cycles in an afternoon to understand a fatigue limit. We bypass the physical wait time.
So the abstraction isn't a defect of the process. It is the core utility of the process.
It is. But the sources we are looking at draw a crucial editorial distinction regarding that utility.
Yeah.
A model is not inadequate because it leaves something out. Exclusion is the entire point.
Right.
A model becomes dangerous when we forget what was left out.
Oh, I am stuck on that phrasing, when we forget what was left out. Because, building a simulation requires a massive amount of explicit definition.
It does.
We have to define the intended purpose. We lock in our assumptions. We establish boundary conditions. We are intentionally choosing which variables to include, like the tensile strength of the steel, and which interactions to exclude, like the possibility of galvanic corrosion because someone accidentally dropped a brass washer into the assembly.
We literally tell the model to ignore the messy variables so we can solve the math. But then we develop amnesia about our own filters.
Yes.
And this is where the National Institute of Standards and Technology, NIST, provides a very stark caution. They warn that an impressive numerical fit alone does not guarantee that a model adequately represents the underlying physical data.
Okay, I want to break down that NIST warning because I've been in design reviews where someone flashes a scatter plot on the screen. The data points loosely cluster around a trend line, and the R-squared value is something like 0.98.
And the whole room just visibly relaxes.
Right. High numerical fit, the math works, it feels like an empirical green light.
Because our brains are desperate for that single summary number. It is cognitively cheap to look at a 0.98 and declare victory. But NIST recommends that we must examine the residual behavior.
Okay, so the residuals. The difference between what the model predicted and what the data actually did.
Exactly. You don't just look at how well the model predicted the hits. You have to look at the shape of the misses. Where did the model fail?
Yeah.
Are the errors completely random, just the expected noise of the universe? Or is there a distinct pattern to the misses?
Because if there's a pattern.
If there is a pattern in what your model got wrong, say, it always overestimates the stress at high temperatures, or it always underestimates the vibration at a specific RPM that is a screening signal. It means there is a physical reality, a distinct force or interaction that your model has excluded, and that physical reality is actively acting on your system.
Let me see if I can map an analogy onto this. It's like tracking a budget, right? If my monthly expenses deviate from my spreadsheet by a few dollars randomly every day, that's just the noise of living. Maybe a coffee costs a few cents more.
Sure, random variation.
But if I am missing exactly $45 every single Tuesday at 3 p.m., that isn't random noise. That's a pattern. That's a subscription I forgot I have. Or a parking ticket I keep getting. The model of my budget excluded a variable that reality is enforcing.
That is a perfect analogy. And in engineering, that $45 discrepancy is a harmonic resonance you didn't model. It's a thermal gradient you assumed was uniform but actually isn't.
Wow.
So the critical questions a team must ask themselves when looking at their own models are, what specific decision is this abstraction intended to support? Which behaviors must it absolutely represent to be useful? Under what specific boundary conditions should its predictions be trusted?
And crucially, what evidence would challenge its adequacy?
Yes.
Because if I can't articulate what physical evidence would prove my model invalid, I have left the realm of engineering. I'm just doing theoretical mathematics in a vacuum.
Yeah.
It's intellectually stimulating, sure, but it isn't building a dependable system.
Which is the threshold we eventually have to cross. Models organize our knowledge safely, but eventually the simulation has to become a physical object. The drawing has to become metal and plastic.
Right.
This is the moment reality joins the design review.
Okay, let me play the advocate for the analytical side again, though, because I understand that models have blind spots, but must every single design question be tested physically?
Whoa.
If finite element analysis proves mathematically that a specific bracket can hold a specific static load, and my pad model places the fastener with 3 millimeters of clearance, when does physical testing cross the line from rigorous to just grossly inefficient? We have these computational tools for a reason. Shouldn't we trust them to handle the baseline physics?
You don't need to drop an apple every time you design a table to verify gravity. We don't need to physically test every mathematical certainty. But we have to understand the temperament of reality.
The temperament.
Yeah, the sources make a beautiful observation here. Reality is not cynical. It isn't actively trying to reject your elegant idea or sabotage your career. It is simply unwilling to approve your assumptions without testing them.
Because reality is the entity reintroducing all the excluded variables we left out of the simulation.
All of them, all at once. The model assumed a perfectly uniform material structure. Reality introduces the chaotic grain structure that happens when you mass-produce a part via die casting, instead of machining it from a pristine billet in a lab.
Oh, yeah.
The model assumed a constant ambient temperature. Reality introduces cyclic heat, which causes thermal expansion, which induces localized stresses that your static linear model completely ignored.
Reality introduces friction, wear, gravity, contamination, fatigue. It introduces operators whose hands are tired.
It introduces, as the sources phrase it so perfectly, Tuesday afternoon.
Tuesday afternoon, I love that because the model never assumes it's raining, or the operator has a cold, or the lighting in the factory is dim, or the floor is vibrating because a heavy forklift just drove past the assembly station.
Which leads us to a phenomenon that really plagues interdisciplinary engineering. A design being locally correct, but globally inconvenient.
I am fascinated by this concept of local optimization leading to global failure. How does that manifest when multiple teams are involved?
Okay, picture a complex system. Maybe a new industrial automation robot, where different engineering disciplines are working simultaneously in their own silos.
Sounds standard.
Right. So the electrical team designs a cable route through the chassis. They calculate the resistance. They optimize the shielding to prevent electromagnetic interference. They calculate the exact thermal dissipation of the wire gauge. From a purely electrical standpoint, the design is flawless. The electrons are behaving exactly as modeled. It is locally correct.
Meanwhile, the structural team is designing a support bracket for that exact same quadrant of the chassis.
And their work is equally brilliant. The load paths are elegant. The stress concentrations have been smoothed out. The material choice maximizes strength-to-weight ratio. From a structural standpoint, it passes every FEA check.
Yep.
Locally correct. Then, the industrial design team creates an external enclosure that is sleek, meets all ergonomic standards, and looks fantastic in the marketing renders.
Locally correct.
Exactly. So every individual discipline has a green checklist. But then, the parts actually arrive at the integration facility.
Then they try to build it.
And suddenly, that mathematically perfect cable route needs a bend radius that requires an extra 12 millimeters of space. Space that the mathematically perfect structural bracket is currently occupying.
Oh, no.
Furthermore, the bracket itself, which held the weight perfectly in the simulation, is now being stamped from sheet metal at production scale. And the residual stresses from the stamping process cause it to flex in a way the idealized model didn't predict.
And what about the sleek aerodynamic enclosure?
Oh, it has a service panel perfectly labeled, service access, unobstructed. But when you open that panel, it travels exactly 15 degrees before slamming into the real physical cable harness that was invisible in the enclosure team's isolated CAD environment.
So the electrical model was right, the structural model was right, the enclosure model was right. But the maintenance technician still needs 3 hands and a diplomatic relationship with physics just to change a simple sensor.
Exactly. Each discipline was mathematically correct within the artificially constrained boundaries of their assumptions. But reality doesn't respect interdepartmental boundaries.
No, it doesn't.
Reality forces all the excluded variables from all the different disciplines to meet in the exact same physical coordinate at the same time. And when they do, the physical system becomes globally inconvenient.
This transition, when the physical system fundamentally contradicts the elegant model, is a very precarious moment for an engineer's psychology.
It really is.
Ego enters the chat. I mean, you spent 6 months developing this model. The slide deck for the preliminary design review was beautiful. All the arrows pointed in the right direction. And now the physical machine is vibrating violently on the test stand.
The language an engineer uses in that exact moment reveals their entire professional maturity.
Because if I'm standing there and the machine vibrates when my model said it would be perfectly still, my immediate human instinct is to defend the model. I might say, is disagreement with the model necessarily evidence that the model is poor?
Right, you look for excuses.
Exactly. Maybe the material batch was contaminated, maybe the test environment wasn't calibrated correctly, maybe the technician assembled it wrong.
It's not about immediately assuming the idea is fundamentally broken, though. It's about recognizing the hierarchy of evidence. The inexperienced response to that unexpected vibration is defensive. They look at the machine and say, but it should work. Or they turn to the tech and say, why isn't it behaving as designed?
It should work. I mean, that is basically a plea to the laws of thermodynamics.
Think about the semantics of the word should in that context. Should describes our expectation. It describes the model's prediction. The machine, however, is describing the actual event. The machine is the objective narrator of physical reality. Arguing with the machine does not improve the measurement.
The machine doesn't care about your R-squared value.
Not at all. So the experienced engineer hears that unexpected vibration, and they don't say, it should work. They step closer, they look at the physical evidence, and they ask, what is it actually doing?
The shift from it should work to what is it actually doing is massive.
It represents the transition from predicting what will happen to observing what is happening. It is the leap from authorship to responsibility.
Authorship to responsibility. Wow.
Yeah, when you are the author, you aggressively defend your expectation because the model is an extension of your intellect. When you take responsibility, you investigate the physical evidence because your primary allegiance is to making the system function.
The sources drop a fantastic line here. They say the most useful sentence in engineering is rarely, "I was right."
It is almost always, that's interesting.
That's interesting, because an idea that survives only by aggressively ignoring inconvenient physical evidence is no longer engineering. If you have to pretend the vibration isn't happening to keep your model valid, you aren't designing a solution, you are defending a fantasy.
And this psychological shift is exactly why we build prototypes. If what is it actually doing is the most important question, then a prototype is the physical manifestation of that question.
Let's explore prototyping deeply, because I want to push on the concept of evidence. We agree models have limits, and physical reality exposes them. A prototype provides confidence that an idea functions in the physical domain, but prototyping is slow.
Very slow.
And it's expensive. We can't machine a new physical iteration every time we change a tolerance by a micron. So how much physical evidence is actually enough? When have we learned enough to stop building models and start building product?
That depends entirely on how an organization defines the purpose of a prototype. Many organizations treat a prototype as just a smaller, earlier product. They build it to demonstrate to management or to investors that the core concept functions. The sources classify this as a weak prototype.
A weak prototype.
Yes, a weak prototype actively seeks approval. Its architecture is designed to generate confidence.
It's the demo model. It's highly polished. It works flawlessly under one very specific, highly controlled set of environmental conditions, and everyone in the room prays no one asks it to do anything outside the script.
Right? Don't touch the red button. But a useful prototype has a completely different epistemology. A useful prototype actively seeks disagreement. Its entire purpose is to expose uncertainty before that uncertainty becomes permanent, expensive infrastructure.
Exposing uncertainty before it becomes infrastructure. I mean, because once it's infrastructure, once you've bought the tooling, signed the supplier contracts, and locked the assembly line, discovering an excluded variable costs a fortune.
A useful prototype isn't built to prove the math was right. It's built to reveal what the math was incapable of knowing. What happens when physical contact occurs between these two unyielding materials? Can this internal geometry actually be reached by a human hand?
Right.
Do the manufacturing tolerances accumulate favorably, or do they stack up and create a mechanical jam? Does the chosen elastomer actually survive the ultraviolet exposure we forgot to include in the simulation?
The sources provide a highly specific illustration of this that I just can't stop thinking about. Imagine a maintenance document for a new system. The procedure specifies, tool required, standard wrench.
A completely rational, seemingly innocuous requirement.
Totally. The CAD model confirmed that a standard wrench fits perfectly onto the head of the fastener. The geometry intersects perfectly, so they build the physical prototype. The technician walks up to the assembly with a standard wrench. In fact, just to be thorough, they try 3 different brands of standard wrenches.
Love a thorough tech.
Right. And all 3 fit onto the fastener individually. The requirement of fitting is met, but none of them have the physical clearance required to actually sweep through the arc necessary to rotate the fastener.
It perfectly encapsulates the chasm between an idea and a physical object. The model knew the wrench would statically fit on the nut. A simple collision detection algorithm can verify that.
Easy.
What the model did not know, what it couldn't know with that incredibly complex kinematic human factors simulation, is that the human hand requires a dynamic swept volume of space to apply torque. The drawing was correct. But the world had comments.
The world had comments. And the critical takeaway is how we view that failure. The prototype didn't fail the idea. The prototype answered the idea. The idea proposed a theoretical maintenance procedure. The prototype asked physical reality if that procedure was possible. Reality said no.
It's just answering the question.
Exactly. That is not a failure of the project timeline. That is the successful acquisition of vital knowledge.
And acquiring that physical knowledge forces us to formally evaluate the design. We've modeled the math, we've prototyped the physical friction, now we have to judge it. But evaluation is not a single, monolithic pass-fail metric. This brings us to a crucial distinction made by NASA's systems engineering framework. We have to meticulously separate verification from validation.
Verification versus validation. I want to spend significant time here. At first glance, it sounds like bureaucratic semantic jargon, but it is fundamentally about the difference between doing things right and doing the right things.
It might be the most consequential distinction in all the systems engineering.
Let me set up the perspective of the model advocate again. We spend months developing incredibly strict, mathematically derived requirements. We specify the dimensional tolerances, the exact weight limits, the peak power draw, the thermal dissipation rates.
All the specs.
Right. And if we build the physical product and the quality assurance team goes down our checklist and every single box is green, the product perfectly matches every single specification we documented, haven't we succeeded? Isn't a fully green checklist the empirical definition of engineering success?
A fully green checklist is the definition of verification. Verification asks a highly specific, legally bounded question. Did we build what was specified? Does the physical product conform to the written requirements? It is entirely focused on conformance.
Okay, so what does validation ask?
Validation asks a much more dangerous question. Validation asks, is what we built actually suitable for its intended use? Does the model we use to generate those requirements accurately represent the real world for the person who actually has to operate the system?
So verification is, did we build the thing right? Validation is, did we build the right thing?
Exactly that. Verification is like following a complex baking recipe perfectly.
Yeah.
You measured the flour to the gram, you calibrated the oven to the exact degree, you timed the bake to the second. The cake is perfectly verified against the recipe.
Okay.
Validation is asking whether the person you are serving it to has a severe peanut allergy.
Wow. The cake was built perfectly, but the user experience is catastrophic.
The gap between conformance and suitability is where some of the most spectacular engineering failures in history reside.
Let's explore how that gap opens up. How is it possible for a complex product to conform beautifully to its requirements, to pass rigorous verification, and still completely disappoint the person depending on it in the field?
It generally happens for one of three reasons. First, the specification itself might have been deeply incomplete. You verified the product against a list, but the list was missing crucial information about the physical world.
That makes sense.
Second, the operating environment might have shifted between when the requirements were written and when the product was deployed.
It passed the vibration tests in the lab, but the lab isn't mounted to the chassis of a mining truck.
Exactly. And third, and this is the most insidious mechanism, perfectly valid requirements can cannibalize each other to create a completely invalid experience.
Wait, I'm struggling to see how that's possible. If requirement A is logically sound and requirement B is logically sound and both are met, how do they create an invalid experience? Are you saying the requirements are physically conflicting in space?
Think about the physical implications of requirements. Let's imagine the requirements for a sensitive piece of industrial diagnostic equipment. Requirement A states, the primary sensor component must be completely isolated from ambient chassis vibration to prevent false readings.
Okay, very reasonable.
Requirement B states, the primary sensor component is a consumable and must be rapidly replaceable by a field technician. Both are completely valid logical requirements.
It makes perfect sense. Protect the delicate part, but make sure we can swap it out when it wears down.
So the design team executes. To meet requirement A, they house the sensor deep inside a heavy, reinforced, kinetically dampened structural casing. Verification check.
Yeah.
Is it secure from vibration? Yes.
Green light.
To meet requirement B, they ensure the casing is assembled with standard bolts, not permanent welds. Verification check. Can be replaced? Yes, theoretically, if you unbolt it. Green light. Verification is complete.
I see the trap closing.
The product goes to the field. Validation time. The intended use case dictates that a technician needs to swap this consumable sensor during a standard 30-minute maintenance window between shifts. But because of how securely it was encapsulated deep in the chassis to meet the vibration requirement, the technician discovers they have to spend 4 hours disassembling the entire superstructure just to reach the component, which they then swap in 6 minutes.
The checklist was entirely green. Both requirements were definitively verified, but the user experience is completely invalid. The design is a failure for its intended use.
And this illustrates why requirement compliance cannot be the end of engineering observation. NASA explicitly states that validation determines how accurately a model represents the real world from the perspective of its intended uses. If the intended use involves human maintenance and your model excluded the biomechanical reality and time constraints of the human, your model is invalid. It doesn't matter how beautiful the math is.
Which brings us to the people who actually hold the wrenches. If validation is ultimately about evaluating intended use, then the ultimate arbiters of that use are the human beings operating and maintaining the system on the ground, the technicians and the operators.
They provide the final reality check.
Now, I have to challenge this on behalf of the analytical mindset. Human memory is notoriously faulty.
It is.
Human perception is incredibly subjective. If a technician tells me a machine is, I don't know, running a bit hot, but my calibrated thermal sensors on the digital twin say the thermal dissipation is well within the calculated operational parameters, shouldn't I trust the calibrated mathematical model over the operational anecdote? I mean, humans are terrible witnesses. Can't anecdotes mislead us just as easily as a bad simulation?
You are absolutely right to be cautious. Reality does not provide complete, objective answers automatically just because a human observed it. Human measurements contain massive uncertainty. Operational anecdotes can absolutely be misleading.
So we shouldn't just blind trust them.
Right. A technician might say the machine is running hot because the ambient air conditioning in that specific wing of the factory is broken that afternoon, or because they are standing near the exhaust port, not because the internal components are actually failing.
So we shouldn't just throw out the telemetry data the moment someone complains.
Never. Engineering is not merely trust whatever you see. It is the discipline of learning how to see rigorously. A single observed event shouldn't automatically overthrow a validated mathematical principle. Tests need controls. Evidence needs context. Measurements need statistical interpretation.
But if we dismiss the operator entirely,
If we dismiss them, we lose the only sensors we have for the unmodeled variables. Technicians and operators are not just downstream recipients of a finished product. We cannot treat them as just the personnel who happen to be standing near the machine when the engineering team is done with it.
right.
They are vital, indispensable observers of the system operating under conditions that the design office simply cannot fully reproduce.
They are the ones actually living in the Tuesday afternoon.
They are. They discover what the system actually does when it's coated in dust, when the bearings are worn, and when the operational textbook goes out the window.
Let's talk about some of those real-world interactions that only operators reveal. The sources give some incredibly frustrating and painfully real examples of what happens when the model assumes a polite reality.
The polite reality. The design office often models a machine failing politely in a well-lit, climate-controlled workshop with the power turned off.
Right, like, please schedule your catastrophic breakdown between 9 a.m. and 5 p.m. so we can observe it cleanly.
But the operator is the one who discovers that the diagnostic indicator light, the very light specifically designed to tell you what's wrong, is physically hidden behind a moving armature when the machine is in its actual failure condition.
You're kidding?
No, because the digital model confirmed the light would illuminate when the voltage dropped. The operator knows you can't actually see the light when the machine is jammed.
Or consider torque specifications. The CAD model says, apply 50 Newton meters of torque to fastener number 4. The technician is the one who discovers that 50 Newton meters is physically impossible to apply at the available angle with a standard human shoulder and elbow. The vector math works, but the biomechanics fail.
And my personal favorite, a classic failure of human factors engineering. The technician discovers that two electrical connectors, which carry completely different voltages and should never ever be crossed, fit together equally well.
That is an absolute nightmare. The model just labels them connector A and connector B. It verifies that they are electronically distinct, but it doesn't realize that in the dark, upside down, a tired operator at the end of a 12-hour shift can easily plug connector A into receptacle B because the physical plastic housings are geometrically identical.
If two things shouldn't fit together, physical reality demands that you make it geometrically impossible for them to fit together. A software model won't instinctively tell you that. An operator plugging it in backward will. This knowledge, the obscure diagnostic light, the impossible torque angle, the dangerous connectors, the 4-hour disassembly for a 6-minute part, this is not secondary feedback. This is primary design evidence.
So To synthesize all of this, the limitations of the models, the friction exposed by the prototypes, the rigors of verification and validation, and the vital human factors engineers have to fundamentally change how they view their relationship to their own work. There is a philosophical shift that must occur in the culture of a design team.
It's a shift from ownership to stewardship.
Let's explore that distinction. Falling in love with the idea encourages ownership. Falling in love with reality encourages stewardship. What is the practical difference in the day-to-day operations of an engineering team?
Ownership is fundamentally defensive. When you fall in love with your elegant idea, your beautiful CAD model, your perfect math, you start asking yourself, how do I protect my solution from criticism?
Right.
When contradictory evidence arrives, when the prototype cracks under stress, or the technician complains about the access panel, it feels like a personal attack on your competence. You defend the expectation. You fall back on, but it should work.
You start viewing physical testing as just a final, annoying, bureaucratic gate you have to pass through before release, rather than a place to actually learn about the system.
Exactly. But stewardship asks a fundamentally different question. Stewardship asks, what does the system need to function in reality? You aren't protecting your idea. You're protecting the outcome.
And under stewardship, when physical reality pushes back, it isn't an attack. The design becomes something the entire team is learning about together, rather than a thesis the author is defending alone. Failure actually becomes a highly useful metric.
Especially when it occurs early, visibly, and safely. A structural failure in a prototype isn't a disaster. It is a massive success for the project because it generates concrete knowledge about a physical limit before that knowledge becomes embedded in thousands of shipped units.
To make this philosophical shift deeply practical for you listening right now, the sources provide a phenomenal framework. They outline 10 questions for a reality review. This isn't a checklist you just tick off. It's a diagnostic tool for organizational culture.
It's essential.
Before we accept an elegant solution, before we sign off on the beautiful simulation, we need to weave these questions into our design reviews to ensure we are practicing stewardship, not just ownership.
The first question is foundational to everything we've discussed. Which assumptions make this design work? You have to aggressively make the invisible visible. What did the model assume about material isotropy, ambient temperature, user behavior, and load cycles?
And following that, which operating conditions have actually been physically observed? Have we only seen this mechanism run in a pristine lab environment? Or have we seen it operate covered in mud, vibrating at high frequency? We have to map our domain of validity.
Then you must ask, what evidence could prove the idea inadequate? Again, if you cannot articulate what physical evidence would prove your model wrong, you aren't testing it. You are just validating your own bias.
I keep thinking about how we verify assemblies in CAD. We use infinite access virtual tools. We literally ghost our virtual camera right through a solid cast iron engine block to look at the threads on a bolt.
Yeah.
We forget what we excluded from the model, so we have to explicitly ask, what has been simplified or excluded? The friction, the cable harness, the thermal gradients.
And that leads directly to the physical assembly. Can the product be assembled with real tools, not infinite access virtual tools, but physical wrenches held by physical hands, requiring a swept arc of space in finite, constrained environments?
What about when it's running? Can it be inspected during operation? Does the diagnostic light actually stay visible when things go catastrophically wrong? Or is it obscured by the very component that failed?
But when it does fail, can common failures actually be diagnosed by the operator? Does the system provide telemetry that tells the technician what's wrong? Or does it just silently stop working, leaving them to guess?
We have to interrogate the maintenance path. Can replaceable parts genuinely be replaced? Remember the 4-hour disassembly for the 6-minute consumable part? Is the maintenance pathway we designed in the software actually executable in physical reality?
We also need to leverage the human sensor network. What would an operator notice before the dashboard indicates a failure? Dashboards rely on digital sensors, which can fail or drift. But what does the machine sound like, smell like, vibrate like before the warning light comes on? The operator knows the baseline hum of the machine. They know when the pitch changes.
And the final question, which might be the ultimate reality check for any engineering team, what did the prototype teach us that the PowerPoint presentation did not?
That is the delta. The presentation was the idea proposing a theoretical reality. The prototype was physical reality answering back. What was the exact difference between the two?
The core argument running through this entire deep dive is beautifully structured. It builds a complete epistemology of engineering. Ideas propose possible systems. Models make selected relationships easier to examine and manipulate. Prototypes ask physical questions and make our assumptions observable. Tests compare our mathematical expectations with physical evidence. Verification evaluates conformance to the written requirements. Validation evaluates suitability for the messy, intended use. Operators and technicians reveal the crew behavior under unmodeled conditions.
And the discipline of engineering is the continuous, rigorous act of connecting all these forms of knowledge.
Good engineering is not the abandonment of imagination. We aren't saying theoretical modeling is bad. Good engineering requires both representations, the beautiful models, the elegant mathematics, and rigorous reality checks. The technical drawing tells us what we intended to make. The physical object tells us what we actually made.
And that difference, that gap between intention and physical reality is not an embarrassment. It isn't a failure of intellect. It is the most critical, actionable information you can possibly gather.
We don't abandon theory. We give theory the ultimate dignity of being physically tested. We allow the physical world to answer our mathematical hypotheses.
Because an idea that was perfect on a screen is just a hypothesis. It's when we build it, and when physical reality joins the review, that engineering truly begins.
Which leaves us with a final, provocative thought to haul over. We've established that reality completes the design. It exposes the missing variables, the friction, the tolerances, and forces the idea to adapt. But reality isn't static. Reality is constantly changing. Wear accumulates on bearings. Materials fatigue over millions of cycles. The operating environment shifts as climates change or operational profiles are updated. Tuesday afternoon eventually becomes Friday midnight in a snowstorm.
The boundary conditions of physical reality are in a state of constant entropic flux.
Exactly. So if reality is what completes the design, and reality is constantly changing, generating new physical evidence with every single maintenance cycle and every single operator interaction, well, at what point does the design process actually end? Is a physical product ever truly finished, or is it in a continuous state of reality review until the day it is retired?
If you embrace stewardship, you realize the design process never ends. It's not a destination, it's a continuous, evolving conversation with the physical world.
Something to ponder the next time you were looking at a perfectly pristine, shadowless CAD model. We want to thank you for joining us on this deep dive. Until next time, keep observing what reality is actually doing.